In this video, we're continuing our discussion of different methods for solving ordinary differential equations. So we were going through different solution methods for initial value problems. And in this video, we're going to discuss the last method, which are the Runge-Kutta methods. So the Runge-Kutta methods were developed by German mathematicians C. Runge and M.W. Kutta. They're essentially generalizations of all of the previous methods. So consider again our initial value problem. dx dt is equal to a function of x and t. So if we assume that the value of the dependent variable x is known at an initial value ti, then Runge-Kutta methods employ the following general equation to calculate the value of x at ti plus 1. So the xi plus 1 is equal to xi plus h, which is our step size, times phi, where phi is a function of the form alpha 1 k1 plus alpha 2 k2 plus alpha 3 k3 up to alpha n kn. So here these alpha j are constants, while the kj are functions of x and t and are evaluated at points within the interval between xi and xi plus 1. And these k's have the form shown here. So k1 is equal to f evaluated at xi ti, k2 is equal to f evaluated at xi plus q11 k1h, and ti plus p1h, up to, and you can see how this repeats here, where these q's and p's are constants that can be determined for the different Runge-Kutta methods, as we will discuss. So the constants alpha j and the forms of kj are obtained by equating the value of xi plus 1 obtained using the Runge-Kutta equation to a particular form of the Taylor series. The k's are recurrence relationships, meaning that k1 appears in k2, and that appears in k3, and so forth. So this makes the method efficient for computer calculations, and the error in a particular form depends on how many terms are used. Now, in this course, in this chapter, we're not going to go through how to come up with the different alphas and k's. We'll just present a few of the more common examples. So the general forms of these Runge-Kutta methods can be either implicit or explicit. So for example, the explicit Euler method is a Runge-Kutta method with only one term, where alpha 1 is equal to 1 and k1 is equal to f of xi and ti. The Hune's method is a Runge-Kutta method with these non-zero terms. So alpha 1 and alpha 2 are equal to 1/2. k1 is equal to f at xi and ti, and k2 is equal to f at xi plus h k1 and ti plus h. Similarly, the midpoint method is a Runge-Kutta method with these non-zero terms as shown here. So alpha 2 is equal to 1, k1 is equal to f at xi and ti, and k2 is equal to f at xi plus h over 2 times k1, and ti plus h over 2. So you can see for each of these that this sort of recurrence relationship, so the k1 appears in k2, and same with here, k1 appears in k2. And if we had more, they would continue on like that as well. So the most popular Runge-Kutta method is referred to as the classical Runge-Kutta method or the fourth order Runge-Kutta method. And it has the form shown here. So x at I plus 1 is equal to xi plus h over 6 times k1 plus 2k2 plus 2k3 plus k4, where k1 is equal to f evaluated at xi and ti, k2 is equal to f evaluated at xi plus h over 2 k1, and ti plus h over 2, so at this intermediate point here, and then k3 is equal to f evaluated at xi plus h over 2 k2, and ti plus h over 2, and then k4 is equal to f evaluated at xi plus h k3, and ti plus h. So you can see that we basically evaluate these four intermediate points or intermediate function evaluations every time we at each time step. So we use all 4 of these to help us go from xi to xi plus 1. And the error in the 4th order Runge-Kutta method is similar to that of the Simpson's 1/3 rule, with the local error term of order h to the power 5, which translates into a global error of order h to the power 4. So this method has much higher accuracy than the methods that we've talked about previously. So the method is termed 4th order because the error term is directly proportional to the step size raised to the power of 4. So let's look at this example that we've considered in the previous sections using this classical Runge-Kutta method with h is equal to 0.4 in this case. So again, recall our initial value problem. Dx dt is equal to tx squared plus 2x. So here our f of x and t is equal to tx squared plus 2x. Our initial condition is that x0 is equal to minus 5, and we want to find the values of x for t up to 5, and here we're going to take a step size of 0.4. So with our values, we can calculate all of the values of k1, k2, k3, and k4 for our first time step. So k1 is just evaluating the function at x0 and t0, which is evaluating the function at minus 5 and 0, which is equal to minus 10. K2 is now evaluating at our function at x0 plus h over 2 k1 and t0 plus h over 2. So plugging these in, we're evaluating the function at our x is going to be minus 5 plus 0.2 times minus 10. So this goes in here. And the 0.2 comes from that h is equal to 0.4. So h over 2 is equal to 0.2. And then for the time, we're evaluating it at t0 plus h over 2. So t0 is 0 and h over 2 is 0.2. So plugging all of our values into our function, we see that k2 is equal to minus 4.2. Now k3 is equal to the function evaluated at x0 plus h over 2 times k2 and t0 plus h over 2. So just simplifying that down, we're going to evaluate with x as x0 plus h over 2 k2. So this k2 goes in here, and we still have our h over 2 is 0.2 and our x0 is minus 5. And then for the time, it's again t0 plus h over 2, so 0 plus 0.2. So plugging that into the form of our function, we get that k3 is equal to minus 4.8589. And then k4 is equal to f evaluated at x0 plus h k3 and t0 plus h. So just simplifying that out, we have x0 plus h this time, so 0.4 times k3, so our k3 goes in here, plus, so that's where our x is, and then our t is at t0 plus h, so 0 plus 0.4. So plugging that into the form of our function, we find that k4 is equal to 5.3981. So now x1 is equal to x0 plus h over 6 times this combination of our k's, k1 plus 2k2 plus 2k3 plus k4. So we can just plug in all of our values that we calculated on the previous slide, and we find that x1 is equal to minus 6.51465. So we can continue on marching it through time to find all the values of x up to, in this case, t is equal to 5.2. And this is the output from MATLAB showing the estimates along with the exact function. And you can see even with h is equal to 0.4, we get a very good estimates for this whole function. Even in this area of rapid change here, we're getting really good estimates here. So comparing this with the explicit Euler method, you can see that for h is 0.1, that we get much better results using the Runge-Kutta method compared to the explicit Euler method. And if you recall, the order of the error here for this one is order h4, where the explicit Euler method was just order h. So that makes sense that we're getting much more accurate results. We can also note that MATLAB has many ODE solvers, and the most commonly used one is called ODE 45, which can be called with the syntax here. So the output is the time and y, assuming that that your function is like has dy dt in it, for example. ODE fun is the function handle of your function, which accepts those inputs, t and y. T-span is the time interval that you're interested in, and then y naught is the initial value. So it's set up to solve initial value problems like this. And it is partially based on the Runge-Kutta formula. It is not exactly the same, so we don't get exact same results as our implementation of this method, but it is based on something partially based on the Runge-Kutta formula. And so for this example, we can compare our fourth order Runge-Kutta with this ODE 45, where h is equal to 0.3. And we see that both of them provide a very good estimate of the exact solution, and they provide essentially the same results, except for in a couple of points where there's some slight differences between the two approaches.